In this video, we will discuss carbon-13 NMR. So first, we'll go over the general principle of carbon-13 NMR. Follow, we'll talk about the signal characteristics of carbon-13 NMR, as well as some of the special techniques that we use in carbon-13 NMR. So first, proton NMR and carbon-13 NMR share many similar principles, but then there are a few major differences. First, carbon-12 NMR do not have magnetic property to them, so only carbon-13 isotopes do. So for every carbon-13 isotope that we have in a molecule, it will give us a signal. And because the percentage of abundance of the carbon-13 is pretty low, only 1.1%, therefore carbon-13 to carbon-13 coupling is normally not observed. And the reason why is as follows. If two carbon were to be bonded to each other, if one carbon happened to be a carbon-13, what would be the chances that the next carbon will be another carbon-13? Pretty low, right? So therefore, carbon-13 coupling is normally not observed. However, we see that carbon-13 and hydrogen can actually couple to each other. But the carbon-13 nucleus is not split by only one hydrogen that is directly connected to it, but it also gets split by the hydrogen that are in 2 or 3 bonds away, and this leads to many complex splitting patterns, and therefore it makes NMR signal not as useful. In order to make carbon-13 NMR data and signal become meaningful, we have to use some special techniques along with it. And the 3 special techniques that we will discuss here in this class are first, broadband decoupling, and second, off-resonant decoupling, and third, distortionless enhancement by polarization transfer, or we call this DAP. So these are the 3 basic techniques that we will go over here in this lecture. So first, let's do a quick comparison between carbon-13 NMR and proton NMR. The chemical shift in proton NMR is from 0 to 14 ppm, whereas carbon-13 NMR chemical shift range is from 0 to about 220 ppm. In proton NMR, when we observe a signal, we would analyze the intensity, the multiplicity, and the chemical shifts of the signal, because those are very meaningful. Whereas in carbon-13 NMR, the only thing that we will look at would then be the chemical shift of the signal. And again, the reason is because the multiplicity due to decoupling is normally very complex, and it makes the data become really difficult to read. So therefore, we will not focus on the multiplicity of carbon-13 NMR. And we will be able to do that by employing special techniques that we will discuss in a little bit. So now, let's talk about the first special technique, the broadband decoupling. Broadband decoupling is a very common method that we use in carbon-13 NMR to suppress all of the carbon-13 and hydrogen coupling. And since there's no couplings in carbon-13 NMR, every carbon-13 would then appear as a singlet. And this singlet right here are then characteristic based on the chemical shift. So again, every carbon-13 will give us a signal, and the signal would then be as singlets. And generally, the more hydrogen that the carbon is connected to, then the carbon-13 signal of it would then be more intense. However, there's no relationship between the intensity and the number of hydrogen that it has. So next, let's talk about the second special technique, the off-resonant decoupling. Off-resonant decoupling is a method, although being used, it is not commonly used because it has some disadvantage to it. So in this method right here, when being used, then that when we only see the CH coupling, the carbon-13 to the hydrogen coupling, that are only one bond with each other. For an example, only hydrogen that are connected directly to the carbon will be coupled to each other, but then not a carbon and a hydrogen that are several bonds away. And if we would have a CH3, it will show up as a quartet. And if we would have a CH2, it will be a triplet. And if we were to have a CH, it will be a doublet. And if we were to simply have one carbon without any hydrogen on it, it would then be a singlet. However, the J value for the couplings between the carbon and the hydrogen are pretty large value. Therefore, the signal overlap with each other and making it become very difficult to analyze. So when we see a signal, it is very difficult for us to know whether two signals are part of the same signal or a separate signal because the distance are too far apart from each other. So again, this method right here being used, but not that often because of this disadvantage. The last special technique that we will discuss here in this class is the distortionless enhancement by polarization transfer, or DEP. So there are several types of DEP that being used. There's a DEP 90 and a DEP 35, and there are also a DEP 45 as well. And these are basically special methods that we use to make the signal become more meaningful. For an example, if we were to apply a DEP 90, then that is only when carbon with one hydrogen on them will give up a signal. We will not be able to see the signal for carbon. They have hydrogens, they have 2 hydrogen or 3 hydrogen on them. But again, only carbon with 1 hydrogen on them will show up on this DEP 90. And if we were to do a DEP 135, then if we were to have a carbon with odd number of hydrogen, it would then give us a positive signal. Versus if we would have carbons with even number of hydrogen, that would then give us a negative signal. And carbon with no hydrogen will not give us a signal at all. So in summary as follows. When we have a DEP 35, it would then give us a when we apply DEP 135, if we were to have odd number of hydrogen, they would then give us positive signal. If we would have even number of hydrogen, negative signal. And if there's no hydrogen, no signal over here. And here is an example of a real DEP 135 and DEP 190. So on the spectra above, this is the broadband decoupling spectra right here, in which that all carbon will give us a signal. So in this case, we see 1 carbon, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there will be 11 minimum carbon that we will have here in this molecule. Now please be aware that sometimes we may have 2 carbon that are symmetrical, and they will then give us the same signal. So just because we see 13 signal, it does not mean there are 13 carbon, but they could be more than 2 carbon that are the same, and therefore the signal overlap with each other. When that happens, the signals tend to be a little bit more intense compared to a signal that give up by only 1 carbon. So if we were to now take this spectra and apply a DEP 135 to it, then we would then see the following. We do not see this signal, but we see this signal right here. And again, we see this signal, and we see this signal, and we see this signal, and we see this signal as well. What this then means is that this carbon, the carbon that show up on this positive side, so this will be called the positive side, and this is the negative side. And this is the baseline in the middle. The signal that show up on the positive side will then have odd number of hydrogen in them. So basically odd number of hydrogen. Versus this carbon right here show up on the negative side, meaning they have even number of hydrogen on them. And furthermore, so we can see that this carbon right here have odd number of hydrogen. This carbon here have odd number of hydrogen. And now furthermore, it is possible for us to figure out whether they have 1 hydrogen or 3 hydrogen. In this case, we know this signal right here have 1 hydrogen because they show up on a DEP 90. So if the signal show up on a DEP 90, that means have only 1 hydrogen on it. So therefore, we know this carbon have 1 hydrogen. And this carbon in here, or this carbon which correspond to this carbon, have only 1 hydrogen on it. So that would then imply that this carbon would then have 3 hydrogen, and this one 3 hydrogen, because this signal right here do not show up on the depth 90. And now let's talk about the chemical shift in carbon-13 NMR. The signal, the most important signal characteristic of carbon-13 NMR are the chemical shift. And in fact, that will be the most useful data that we have. When we apply the special technique, most commonly it is the broadband decoupling that being applied. We do not do the depth 90 or the depth 135 that often. But again, a lot of time it is the broadband decoupling, where every carbon will show up as a singlet. And now, what makes them unique would then be the chemical shift. And now let's go over the chemical shift of the carbon in carbon-13 NMR. So if we would have an sp3 carbon and carbon bonded to a halogen, they will show up anywhere between 0 to 50 ppm. So when they connected to the halogen, so let's say X here the halogen, that when they tend to be closer to this 50 ppm right here. And if we were to have an sp1 carbon or carbon that are bonded to nitrogen oxygen, that when they will show up somewhere between 50 to 100 ppm. So again, the sp carbon and carbon that are bonded to nitrogen and oxygen, that will be their chemical shift range. And benzene carbon or sp2 carbon as part of the benzene or the alkene will show up somewhere between 100 to 150 ppm. And lastly, carbonyl is anywhere between 150 to about 200 ppm. And furthermore, the table below shows the chemical shift a little bit more specifically. So in this case, if we were to have a carbonyl in aldehyde and ketone, then there will be about 190 to about 200 ppm. Versus in the carbonyl from the other functional group, then again, they will be somewhere about 150 to about 190 ppm. And benzene ring as follows. So this table right here gives a more detailed chemical shift of the different signal. And when in regard to the chemical shift of alkane or hydrocarbon, so here in this case right here, the more substituted the carbon is, the more the closer they tend to be to the 50 ppm range. So in this case, this carbon is tertiary, and this is secondary, and this is a primary. And the chemical shift of the tertiary carbon tend to be higher than the secondary, and the secondary higher than the primary.